on Lewis dot diagrams and structures for ionic and covalent compounds. So first we're going to start with electron dot structures. These are the chemical symbol surrounded by the valence electrons. And remember, the maximum number of valence electrons is 8. And so you'll see here in nitrogen, nitrogen has 5 valence electrons, 1, 2, 3, 4, 5. And we could go clear over here to argon, and it has 8, 2 on each side. So the max you put on each side, north, south, east, or west, is 2. So how do you know the number of valence electrons in an atom? You count the total number of valence electrons. Well, that sounds like I said valence twice, because I did. So to know the valence electrons, note the group number from the periodic table, and remember the groups are the columns going up and down. For example, group 1A has 1 valence electrons. That means the elements in group 1A all have 1 dot. The elements in group 4A have 4 valence electrons, and in 7A, meaning column 7A, they have 7 valence electrons. Let's take a peek at the periodic table. So here in group 1A, they all have 1 valence electrons. 2A has 2 valence electrons. We don't talk about the B groups, which is the transition metals in here. And then we skip over here to the A's. So 3 valence, 4, 5, 6, 7, 8. Except for helium. Helium only has 2 because it has just 2 protons. It does not have 8 valence electrons. It's too far away. So again, it's the A groupings. The B groupings do not count. Well, it's only one group. The B group does not count for valence electrons. That number in front of it will not tell you how many valence electrons. So how to draw electron dot structures. I think you did this in biology. So you determine the number of valence electrons. And you draw the electrons as dots around the element symbol. It's a little bit like 4 seats on a bus. They can hold 2 dots per seat, and you put it north, south, east, and west. I don't care how you arrange it around there, as long as you don't have more than 2 on each side. So, for example, lithium is in group 1A. It would have 1 dot. Beryllium is in 2A. It would have 2 dots. Boron is in 3A, so it'll have 3 dots, and so on and so forth. And oxygen, I could have spread them out so there was a single one there somewhere. And then fluorine has 7 because it's in 7A, and neon has 8 valence electrons. So you got to know how to do that. And again, the max is 8. So the charge or oxidation number of an atom, we did this when we did naming, can be determined by looking at the valence electrons for most elements. For metals, the charge is equal to the number of valence electrons that the atom will lose to form a cation. So metals lose electrons and they form cations because they lost their negativity, so now they're positive, just like that cat with the paws. And for nonmetals, the charge is equal to the number of valence electrons the atom will gain to form an anion with 8 valence electrons. So the nonmetals gain negativity and they become anions. The metals lose electrons and they become positive. So the metals actually lose their electrons and the nonmetals will gain them. And they share electrons such that they, for the most part, manage to get 8 valence electrons either in their outer shell, or they will lose some such that their next inner shell will have 8 valence electrons. So examples. In group 1A, all the elements have 1 valence electron, and they lose that 1 valence electron, and when they lose one, they become a 1+. And in group 2A, they lose 2 valence electrons, and they become 2+. And in group 3A, not all of them in 3A, they will lose their 3 valence electrons to become 3+, because then in their inner shell, they have 8 electrons, and that is what they're aiming for. And then in anions, so in group 5A, they gain 3 electrons to have an octet. So they have 5 valence electrons and they gain 3 to get 8. So notice this, 5 plus 3 is 8. And they are 3 minuses. The nonmetals in group 6A will gain 2 electrons. Notice that 6 plus 2 is 8. So they have 6 valence electrons. They gain 2 to have an octet of 8. So they become O2 minus, S2 minus, Se2 minus. And then the nonmetals in 7A will gain 1 electron because they have 7 valence electrons. 7 plus 1 is 8. A little tricky there, right? So the Lewis dot structures, visual representations of the bonds between atoms, and include all the valence electrons of each atom. When you look in different places, you'll see these drawn in different ways, but this is how I consider them to be drawn. So you will have your metal. Remember, the metal is always first in an ionic compound, and then we'll have the nonmetal. And the metal transfers its valence electrons to the nonmetal. And sometimes you have multiples of each element such that it will equal out in how many electrons are transferred. So the sodium lost or transferred 1 electron. That's why it is a plus. It's also called a 1 plus, but we don't always write the 1. And the chlorine gained that electron, and now it has 8 valence electrons. So the nonmetal is always written with 8 dots around it. It will always have this set of brackets around it. It's a little bit like it stole that electron, it gained it, it's trying to keep it inside its fences. And since it gained an electron, it will have that 1 minus. So the rules, you determine the number of valence electrons for each atom. You draw the electron dot structure for each atom. You draw them maybe in different colors so you have a visual for it. And then you determine the transfer of electrons from the metal to the nonmetal. And then you draw the compound with the correct number of valence electrons on each ion. The metal will not have any dots around it when it's all finished. The non-metal will have 8 dots around it in brackets and will have a charge. It could be a 1 minus, it could be a 2 minus, it could be a 3 minus. So let's try these. So sodium chloride, electron dot structure. So we start with the sodium, and sodium is in group 1A, so it has 1 valence electron. I drew it on that side because then it will be closer to the chlorine that I'm going to draw over here. And I'm going to draw the chlorine with X's for its valence electrons, just so we can see a difference between those. So chlorine has 7 valence electrons. Sodium has 1. Sodium will transfer that 1 valence electron, happy to give it up because then in its inner shell, from that valence shell, it will have 8 electrons. And so sodium loses an electron, it becomes a plus or a 1 plus, and then the chlorine gains that 1 electron. Again, these are usually written as dots, but I'm writing them like that so you can see, and then we put it in its brackets or its little cage, and it gained 1 electron, and that's the final answer. Let's go on to calcium chloride, CaCl2. So we will draw Ca. Ca is in group 2, so it has 2 valence electrons. Then Cl is in group 7 again, and it has 7 valence electrons. And there's 2 of them. I feel like a horse. Clop, 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 clop. And so each chlorine has 1 vacancy. Calcium will give its first electron maybe to that one, and then it'll give its second electron to that one, such that then kind of an intermediary you would have would be Ca with a 2 plus, and then you will have 2 Cls that now each have 8 dots around it, and they each gained 1 electron, so they're a 1 minus. But that's not how you write the final answer. Since you have 2 Cls, it's a little bit like having an X plus an X. You would write it as 2X, so we're going to write this as 2Cl. So we're going to progress over to here. Ca2 plus, we just keep what we had there. And I'm going to have 2 Cls outside the bracket there. And that means I have 2 Cls. They each had 8 dots around it, and each Cl was a 1 minus charge. It does not add up to a 2 minus charge because Cl is not a 2 minus. Cl is a 1 minus. And I'm going to rewrite this just a little bit so you can see this. Again, dot, 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 dot. So 2 plus must cancel 2 minus to be neutral. Going back to our naming, we have to have neutral. So 2 and that 1 make a 2 minus, and that 2 plus, they cancel out, so it's neutral. So this truly must be the final answer. Moving right along. Now we're going to move on to covalent compounds. Completely different. Covalent compounds are compounds that share electrons. They do not transfer. They are good at sharing. Some elements are better at sharing than others. And so there's lots of different processes for this, and I'm going to just show you a simple process, and I may make another video showing you a different way to do it in case this way doesn't quite speak to your brain. So the first thing we do is determine the number of valence electrons for each atom. Again, look at the periodic table, look at the group number, and they're always in the A-grouped columns. Draw the electron dot structure for each atom, draw them in different colors, maybe if that's what you need for each element, or give one X's and the other one dots so you can separate which part is which. Write the skeleton structure of the molecules. Draw a skeleton for the molecule which connects all the atoms in the compound. Remember that a singular element is usually in the center because there's nowhere else for it to go. And there are some little tricks of the trade here that you will learn the more you do this. So complete the octets for the atoms. So almost all elements want to have an octet or 8 valence electrons, but there's a couple of exceptions. Hydrogen has a duet. Duet means it just wants 2 electrons, and then it will be finished. And boron's interesting. Boron's halfway between the left and the right side of the periodic table, so to speak, so it doesn't want 2, but it can't quite reach 8, so it will be happy with 6 valence electrons. And again, hydrogen will be happy with just those 2. So if all the atoms do not have an octet, example, hydrogen duet, boron is 6, I don't know the fancy word for that one, then you'll make multiple bonds, which is great with covalent bonding. It does not happen with ionic bonding. Remember, they just transfer electrons, and they're held together by an electrostatic attraction. This is different bonding on covalent. So 2 shared electrons equal a single bond. So this HCl really looks like that. Maybe you could draw it like this. Like electron from hydrogen, the electron from chlorine. There's actually more going on in this chlorine than I wrote on there. But in general, we draw it just as a line, and that line represents 2 electrons that are shared. 4 shared electrons equal a double bond. Ooh. And so each line represents 2 electrons, so there's 4 electrons there total. 6 shared electrons equals a triple bond. And again, you have 2, 4, 6. Each line represents 2. There's 3 of them. 3 times 2 is 6. So there are these things called lone pair electrons. These are electrons that are not shared in the bonding. They help each atom add up to 8, or 2 for hydrogen, or 6 for boron, and are important in the structure. You have to have them in your drawing, or you don't get full credit. Example, N2, which is one of those diatomic elements that we have to remember, it always travels in pairs, looks like the following. So you see a nitrogen, and they each have these lone pair electrons and the 3 sets of bonded electrons. So it's those dots that are called lone pair electrons. They're all alone. They're out there, but they really add something important to molecules and how they behave. So let's do some examples. Water. So determine the valence electrons for each atom. So each hydrogen has 1 valence electron. This little diagram's a little wonky. It looks like an antenna there. And 1 oxygen has 6 valence electrons, so 2, 4, and then 6. Those ones are spread out. And then you draw a skeletal structure. The single thing goes in the middle, and then the other elements kind of go around it. Obviously, this diagram is indicating its shape and angle. Perhaps you wouldn't have drawn it like that. Maybe you would have drawn it eventually like this. And if it's covalent, they at least have to have a single bond. And so every element has to add up to 8, or 2 for hydrogen, or 6 for boron. So I'm going to rewrite this down here. So you look at hydrogen. Hydrogen wants 2. Does it have 2? It has 2, so check that hydrogen off. And then I'm going to look at this other hydrogen because it's equal but opposite. That hydrogen thinks it has 2. It's sharing 2, so it has 2 valence electrons, and check it off. Now I'm going to look at the oxygen. I got to rewrite it. So oxygen came with 2, 4, 6, and then each hydrogen brought 1 electron. But oxygen isn't finished. We didn't finish drawing those on there. So when I look just at the oxygen, it thinks it has 2, it has 4, and then it needs its 6, and then it needs its 8. And in this drawing, it's drawn the way it's supposed to be according to this Vesper theory that we haven't learned yet. And so oxygen is single bonded to that hydrogen, single bonded to that hydrogen, and then it has a lone pair there and a lone pair there. They're drawn like that because that's technically how they're supposed to be drawn. But if you don't draw those dots, if you happen to just draw them like this, that is fine. Some more covalent Lewis dot structures. So bonding pairs of electrons. One or more pairs of electrons that are shared to form a bond. They're usually drawn as aligned. And lone pair electrons are electrons that are paired up and are not used to form a bond. They are the lone pair electrons. They're the extra dots on, it could be the inside element, it could be an element on the outside. And again, we went through the single bond, the double bond, the triple bond, and remember that shared electrons can be drawn as aligned, but you don't have to draw it like that. It makes it easier on the eyes. So let's try some of these. Let's do the electron dot structures for diatomic hydrogen. It always travels in pairs. It's one of the have no fear of ice cold beverages. And each hydrogen has 1 valence electron. Where did I get that? From the periodic table, hydrogen is in group 1A, so it has 1 valence electron. I drew them such that their valence electrons were looking kind of towards each other. And so this one has 1 valence, that one has 1 valence. They really want 2, so if they share them, then they each think they have 2. This hydrogen thinks it has 2 valence, not 2 valence, it has 2 electrons, and that hydrogen thinks it has 2 electrons. So the final way we would draw this is H with a line and an H. If you also wanted to draw it with the dot and the line and the dot, that would work also. Let's move on to oxygen. Oxygen's a wee bit more complicated. So each oxygen, we have 2 of them, has 6 electrons. So 2, 4, 6. Let's draw this one as X's. This might get confusing. And maybe I should have separated them out, but I didn't. So this involves a little bit of thinking on your part. So you could go, what if my next step, I took this oxygen and that oxygen, and I took those 2 and I moved them there. Let's try that. So then we would have it looking a little bit like this. And what if I move this one just a little bit closer and just leave that the way it is? Now I'm going to count up my electrons. So this oxygen has 2, 4, 6. That one has 6 electrons. Oh boy. I'm trying to erase these little blue dots and it's not going so well. Let's put that dot back there. And then the next oxygen thinks it has 2, 4, 6, and 8. Well, we want them each to think that they have 8. So this is not what it is. Let's try, so we tried that. Now let's go and try another direction. Let's rewrite this in pink. So we have oxygen. That worked. I'm just drawing those there. I'm going to take a pair of these X's and move them such that they're shared. Let's try that. So if I take a pair of those X's, then I have the top ones and the bottom ones left. Now let's count. So this has 2, 4, 6, 8. I'll show you where that is. There's 2, 4, 6, and 8. So this one definitely thinks it has 8. Now let's count the oxygen on the right. It has 2, 4, 6, 8. Ooh, it thinks it has 8. So that must be what it is. So I'm going to rewrite it. Oxygen has the dots around it. That oxygen has its X's. And then those ones share and those ones share. It probably doesn't matter which way you do it. So then you have this and you have that, and the final answer would probably look a little bit like this. Ooh, in the world. That has 8 and that has 8. We're good. Let's move on. All right, let's do some more practice. Nitrogen. So each nitrogen has 5 valence electrons. 1, 2, 3, 4, 5. 1, 2, 3, 4. Let's do X's. 5. I'm going to sneeze just so you know. Excuse me. So first I'm going to put those two together. So I have those dots, and then I'll have that and an X. And this one will add up to 2, 4, 6. And I'm going to count this next one. It adds up to 2, 4, 6. We want it to add up to 8, so that's not good enough. Let's try this again. What if we just take maybe another pair and throw it in there? So we'll keep that nitrogen like that, and we'll have that dot, we'll have that X, and then we'll do another X and another X, and then we'll keep those X's there. So this first nitrogen has 2, 4, 6, 8. This nitrogen, though, has 2, 4, 6. Not quite there. I think the next thing we do is, we can't take a whole set. What if I take 1 dot and 1 X? Let's try that. I'm drawing my arrow, and then we'll do nitrogen and a dot, and then we'll have that X and that dot and an X and an X. And then we said we were going to take a dot from there, so I'll put that one there, and then we're going to take, I think, an X from there. This looks really wonky. And I think I have an extra X sitting there, do I? I think so. This looks crazy. So what does this really mean? I think then I probably want to combine those two. They need to be together. They can't be separated. I'm going to put that one over there. So I'm going to rewrite this, and I'm going to rewrite it a little bit differently. So we'll have a dot and an X, and we'll have a dot and a dot. And how about I do an X and an X? I see an X and X there, an X and an X there, and a dot there. So 2, 4, 6, 8. 2, 4, 6, 8. They each have 8. This drawing right here is not quite what we want. So we'll do dot, dot, and N, and then we'll do an X and a line, and an X and a line, an X, and then a dot and a dot. We're getting there. Not quite perfect. I think our final answer needs to all be turned into dots. So that'll be a dot and a dot. I actually wouldn't draw these with the dots. It looks like that. And nitrogen has a triple bond. Nitrogen loves to triple bond. It loves to gain 3 electrons because it has 5 valence electrons. 5 plus 3 is 8. So each of these has 8. And each nitrogen has lone pair electrons. So that nitrogen has 1 pair of lone pair electrons because a pair is 2. And that nitrogen has 1 set of lone pair electrons. Let's try CH4. CH4 is a little bit easier. So you always ask yourself, is there a center? If you just have 2 elements, there's not a center. But if you have more than 2 elements, there's a center. The single thing is the center. So the C is going to be the center. And carbon has 4 valence electrons because it's in group 4. And then I'm going to situate each of my hydrogens, probably going to be north, south, east, and west since there's 4 of them. And they each have 1 dot. And this looks perfect. They each share an electron with the carbon, which means they're single bonded. And there you have CH4. It's also called methane, if you didn't know that. It's an organic compound. We transmit methane gas. Animals transmit methane gas. Methane gas is a natural gas found on Earth. Let's do the next one, CO2. Ah, man. So if you're seeing the pattern here, anything that has oxygen or an element underneath oxygen can be a little more difficult. And we have a single element, which is carbon. That's going to go in the center. And I have two oxygens. I'm just going to put one east and one west, kind of one left and one right. My carbon will have 4 dots. Each oxygen will have 6 dots. 2, 4, 6. 2, 4, 6. Remember, the name of the game is we want to share to get 8 valence electrons. So, oh, I should have done these all as dots, but I did. Let's try this. We'll do that, and then I'll take one of those. Ooh, I'm really crisscrossing my applesauce. And I'll take that one. So at least we'll have C with a bond there, C with a bond there, and then we'll have a bond with that oxygen. We have 2 of them. I got to count what's left for each oxygen. 2 and 4. Looks like. So let's count it. 2, 4, 6, 8. 2, 4, 6, 8. So each oxygen has 8. Now let's count the carbon. The carbon has 2, 4, 6, 8. They are all happy, so it looks like this in a better diagram. Bump, 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 bump. Ooh, let's see, it was a little bit ugly. There obviously is another way to do this. I prefer a different way of doing it because to me it's mathematical and it's much easier. I hope this helped. I'll make another video for your worksheets, so look for that video.